Good morning, good afternoon, good evening. Welcome to this last day of the TAUP 2021. My name is Juan José Hernández, and I'm the chairman of this session. We start this session by paying tribute to two outstanding physicists who made key contributions to neutrino physics and unfortunately are not anymore with us. They are Professor Masatoshi Koshiba and Professor Samoil Bilenky. We have the pleasure today to have with us Professor Takaaki Kajita, who will tell us about Koshiba Sensei. Professor Takaaki Kajita, winner of a Nobel Prize in Physics in 2015, is a member of the Institute for Cosmic Ray Research of the University of Tokyo and of the Kavli Institute for the Physics and Mathematics of the Universe. So straight away, I give the floor to Professor Takaaki Kajita.
Thank you. Now, let me share the screen. Okay, you see this photo. This was Professor Koshiba with his 50 centimeter diameter photomultiplier tube. So in this talk, I want to talk about Professor Koshiba. And this is the outline of this talk. First, I have a brief CD of Masatoshi Koshiba before Kamiokande. Then I want to move on to Kamiokande, Kamiokande to Kamiokande 2. And also, I want to mention the initial idea of super Kamiokande and closing remarks. Professor Koshiba was born in Toyohashi City, Japan on September 19th, 1969. He graduated and he finished the undergraduate course at the University of Tokyo in 1951. He got PhD in 1955 at Rochester. The thesis topic was on ultra-high energy phenomena in cosmic rays. Then he moved to University of Chicago, and then in 1959, he joined the cosmic ray emergence experiment at the University of Chicago. Also, in 1960, he was appointed as the PI of this experiment. Then in 1962, Professor Koshiba came back to Japan as the associate professor of the University of Tokyo. And in the 1960s, he carried out an underground muon bundle experiment in Kamioka. And in the 70s, he realized the importance of E plus E minus experiment. Therefore, he joined the DASP experiment and also jointly formed the JADE experiment, both at DAISY. And this is the photo of Professor Koshiba at the muon bundle experiment in Kamioka. Professor Koshiba here. Then I want to move on. There was a workshop on the infinite theory and baryon number in the universe at KK in 1979. Professor Koshiba proposed the initial concept of Kamiokande. That was 20 by 20 by 5 meter water detector with 5-inch photomultiplier tubes. Soon after, Koshiba heard that there was a similar but potentially larger experiment, later known as IMB, was being planned in the United States. Therefore, Professor Koshiba revisited his original design and came up with the idea to develop photomultiplier tubes with 50 centimeter diameter. Koshiba knew Hamamatsu through the JADE experiment. In JADE, 3,000 photomultiplier tubes were used for the electromagnetic shower counters. Koshiba and Hiruma, the president of the Hamamatsu company, discussed. And finally, Koshiba convinced Hiruma to develop 50 centimeter diameter phototubes, which the words that was I had. You are younger than me by 1 day. In this country, younger people listen to the older people. Please listen to me and develop 50 centimeter diameter phototubes. So this way, 50 centimeter diameter photopultiplier tubes were developed. And also I want to say that Koshiba kept the personal connection to the people in the Kamioka mine since his first underground experiment in the 60s. Therefore, he decided to construct the experiment in Kamioka, and the name of the experiment was decided to be Kamiokande. That was Kamioka nucleon decay experiment. And in the spring of '83, Kamiokande members came to Kamioka to construct the Kamiokande detector. And I want to show you 2 photos of Professor Koshiba. And this left one was taken at the mine entrance, and you can see Professor Koshiba at the center. And in the right photo, Professor Koshiba is in the Kamiokande tank. And at that time, we were constructing the Kamiokande detector. Unfortunately, the Kamiokande experiment started taking data on July 6, 1983. Unfortunately, no clear evidence for proton decay was observed. However, Koshiba noted that Kamiokande observed the electron spectrum from the stopping cosmic rays down to 15 MeV, and therefore proposed to improve the Kamiokande detector to observe solar neutrinos. That was in the fall of 1983, only a few months after the start of the Kamiokande experiment. And also Koshiba thought that he needed more collaborators to improve Kamiokande and invited the Pennsylvania group to form Kamiokande 2. And this is the initial spectrum of the electrons from cosmic ray muons. And you can see the spectrum well down to around 15 MeV. And in the right photo, you see 3 happy people who agreed to work in Kamiokande 2. And well, with this idea, the Kamiokande collaboration worked to improve the Kamiokande detector to Kamiokande 2. And in the initial Kamiokande, there was nothing between the steel tank and the surrounding rock. But in Kamiokande 2, we put water between this and the tank and this wall, rock, and install the photo detectors to form the outer detector. Also, the top outer detector and the bottom outer detector were constructed. So there were many hardware improvement works in 84 and 85. Also, there were improvement of water quality in 85 and 86. And finally, Kamiokande 2 started the stable data taking in early 87. And then in February 87, there was a supernova explosion at the Large Magellanic Cloud. And of course, at that time, Kamiokande was taking data, and we looked at the data and then found this kind of data. Here, the horizontal axis shows the time, and the vertical axis is the number of photomultiplier hits, which corresponds to the energy of the event. And then we found this kind of cluster of events. That was the detection of the neutrinos from supernova 1987A. And the photo shown here is the Professor Koshiba at the press conference after the detection of neutrinos. And also, I want to mention the solar neutrino detection in Kamiokande. The main purpose of the Kamiokande 2 experiment was the detection of solar neutrinos. And Kamiokande 2 published the observation of solar neutrinos in 1989. And the observation confirmed that neutrinos were coming from the sun. The energy spectrum was consistent with the prediction. Also, Kamiokande confirmed the deficit of solar neutrinos as suggested by the Homestake experiment. And of course, later, the solar neutrino deficit was concluded to be due to neutrino oscillations. And here, I show the initial solar neutrino data from Kamiokande 2. And because of these contributions, Professor Koshiba, together with Ray Davis, received Nobel Prize in Physics in 2002 for pioneering contribution to astrophysics, in particular for the detection of cosmic neutrinos. And in particular, I would like to show you this photo. This photo was taken in Stockholm. And of course, here is Professor Koshiba, and this person is Teruo Hiruma, the former president of Hamamatsu Photonics Corporation. And he was the person who was convinced to produce 50-centimeter diameter photomultiplier tubes. And Professor Koshiba, remember him. Now, before moving on to the other topic, I want to show you this photo. This was Professor Koshiba in front of the event display. Every morning, Professor Koshiba started working by scanning the new Kamiokande data. They were the candidate contained events. He continued this work style until he retired from the University of Tokyo in March 1987. So we learned a lot from his passion for physics. Now, I want to discuss the initial idea of super Kamiokande. In the fall of '83, Professor Koshiba proposed to observe solar neutrinos in Kamiokande. At the same time, he thought that the event rate of solar neutrinos with the Kamiokande was too low to study solar neutrinos in detail. Therefore, Koshiba proposed super Kamiokande to study solar neutrinos in detail and to search for proton decays. This idea was presented in December '83 in a workshop in KK. And this is the initial drawing of the super Kamiokande. And now if we look at this part carefully, it says fiducial volume 22,000 tons. Now in super Kamiokande, the real fiducial volume is 22.5 kilotons. So super Kamiokande essentially kept the initial idea of Professor Koshiba. And we'd like to thank Professor Koshiba for his pioneering idea. We have been enjoying the neutrino studies with the super Kamiokande for many years. Okay, let me conclude. Professor Koshiba always worked on his research with strong passion for physics and outstanding leadership. We think Professor Koshiba was a great physicist who was able to feel the direction of physics. And finally, I want to convey Professor Koshiba's words. This was for his younger colleagues, but maybe to all of us. He said that we should always have several eggs of research ideas because some of them could hatch in the future. Okay, that's all from me. Thank you very much.
Thank you, Professor Kajita, for this moving remembrance of Professor Koshiba. We now understand not only the determination and his character of Professor Koshiba, but also how important it is to be older by just one day compared to some other people. Thank you very much for this presentation and tribute of Professor Koshiba. So now we go on to the talk of Professor Carlo Giunti of INFN Torino, who will speak about Samoil Bilenky. Professor Giunti?
Yes, can you hear me?
Perfectly.
Very well. So you can see my slides. Good. So you see my slides, right? So I am very honored to present this tribute to Samoil Bilenky. And I would like to thank the organizer, Mariam and Sergio, for the invitation. So first of all, I would like to explain why I'm presenting this tribute. That is because I knew Samoil well. He came to Torino for the first time in 1992, and we soon started to collaborate, and we became also friends. As many of you know, Samoil was a very friendly and kind person, and we spent a long time together. He came to Torino many times, and we meet also in other places all around the world, as you can see here from these pictures. In this short time, I cannot describe all the history and achievement of Samoil, and so I encourage you to read also the obituaries that were presented in the Joint Institute of Nuclear Research News and in the Saint Courier. And there was also in February at the International Workshop on Neutrino Telescope a very comprehensive talk by Sergei Pektov that is available online. So Samoil was born in Ukraine in 1928. He lived his childhood in Ukraine, but he and his family had to leave Ukraine when it was invaded by German troops during the Second World War. And then they went to some place in Siberia, far from the front. After the war, Samoil studied in Moscow and graduated cum laude in 1952 under the supervision of the famous physicist Pomeraniuk. A short time later, he started to work at the Laboratory of Nuclear Problems in Dubna. This was a laboratory that was classified, so this was the time of the Cold War. And this became unclassified only in 1954, and after, in 1956, became the Joint Institute of Nuclear Research. Since 1956, Samoil was a staff member of GINR, and when he was there, he also gave lectures in Moscow. I must say that I spoke with, we were talking about Samoil. He told me many stories, but he considered himself Russian. So most of his story concerned his life in Russia, specifically in Dubna and Moscow. The early career of scientific career of Samoil was devoted to the study of scattering of polarized particles. He considered hadrons and leptons, and he always remained very interested in these topics. And although we wrote most of our papers are on neutrinos, our second paper in '93 was on polarized proton-antiproton scattering. And he was also very interested in the nucleon properties, especially form factors, and we wrote also several papers on them and on this topic. And he wrote also papers on this topic with other people, and mainly with Valerio, which is in Torino. She's here, and this is a picture of Vanda with the wife of Samoil, Sofia Bilenky. Yeah. And this is a picture that we took when we were eating pizza in 2008, eating in Torino. Samoil, most important for Samoil is his collaboration with Bruno Pontecorvo. They were friends since the 50s, and their families, they liked to go around and hiking and camping. But he did not collaborate with Pontecorvo until the 70s. And the first papers that he wrote on neutrinos are on some rather exotic topics, but later in the middle 70s, he started to work with Pontecorvo on the theory of massive neutrinos and neutrino oscillations. And this was a very important contribution to the fundamentals of neutrino physics. And it was important that they joined the deep physical intuition of Pontecorvo and the profound theoretical knowledge and wisdom of Samoil, and led to several important papers that laid the foundations of the theory and the phenomenology of massive neutrinos. In particular, they discussed the foundation of the developed the foundations of neutrinos oscillation in vacuum and of the theory and the phenomenology of massive Majorana neutrinos that are obtained for the diagonalization of the general Dirac plus Majorana mass Lagrangian. These are the important papers on the foundation of neutrino, the physics of massive neutrinos that they wrote in the second part of the 70s. And one must also note the very good and complete, this is the first complete review of massive neutrinos and the neutrino oscillations that was published in Physics Reports written by Bilenky and Pontecorvo. Later, Samoil wrote a really monumental review on the physics of massive neutrinos and neutrino oscillation together with Petrov, and still now one can find very useful things in this review. In the 80s, Samoil continued to work on the physics of neutrinos, and together with other collaborators, mainly Sergei Petrov, he published several fundamental papers on the physics of Majorana neutrinos and the discussion especially concerning the Majorana phases. In those years, he also published a very good review together with Jiri Osek on the neutral currents. After the fall of Soviet Union, Samoil left Dubna and lived mostly out of Russia. And he was always accompanied by his very kind wife, Sofia, that many of you know, because she was very often with him. Sofia was a physicist until 1992 when they were in Dubna. And then after she became interested in art and culture. And so it is always very interesting to talk with her about this. And she also learned to speak well Italian. So in the following years, they spent considerable time in many places. And I remember Barcelona, Munich, Padova, Seoul, Trieste. They came very often to Torino, and then Tübingen, Valencia, and Vienna. And they finally settled in Vancouver, Canada, where their son, Mikhail, that his friend know him as Misha, was already living. And Misha was also a physicist until about 1999, and then he became a brilliant biologist, and then now he's working on the human genome. Misha is also known because he likes to draw cartoons, and these are famous cartoons that appear on the wall of the Pontecorvo office in Dubna. And you can see here, this is a cartoon of the magic of neutrino oscillations performed by Pontecorvo. Misha is also the author of the drawing that are used for the International Pontecorvo Neutrino Physics School. And here you can see the posters with the Misha drawing here. And this is an important school in neutrino physics that was initiated by Samoil Bilenky in 1998. And it is held every 2 years. Here you can see the last edition in 2019 in Sinaia, Romania, and this is the picture of the people participating. The next edition should have been held this year, but it was postponed to next year because we prefer to do it in person. Samoil wrote a lot of papers, and he also wrote 5 books. So the first 3 books were first written in Russian, and then these 2 were translated in English, and then the other 2 were written directly in English. And you can see here the covers. And I suggest for the students this very good book on the physics of massive and mixed neutrinos, of which he wrote a second edition in 2018. Samoil received also several awards. Most important are the Humboldt Research Award in 1999 and the Pontecorvo Prize in 2002, and this is a picture. He had also very well-known PhD students, and in the physics community, mostly well-known and very active are Sergei Petkov and Fyodor Sinkovich. And I would like to end this tribute by just remembering something that about which Samoil taught a lot in the last years, and namely the conjectures about sterile neutrinos. We wrote several papers in the late 90s of sterile neutrinos, especially after the discovery of the LSND anomaly. And you can see among them, most important is this paper that we wrote together with Walter Grimus. And here you can see the handwriting of Samoil. As many of you know, he liked very much to do all the calculation himself by hands. And he typically started by first principle, just by writing a Lagrangian, and then derive all the everything. So this paper is a rather important paper because already at the time we discovered what is called the appearance-disappearance tension in the for sterile neutrinos. That is present in what was later called the 3+1 model. And it is interesting that we wrote this paper in '96, but we managed to publish only 2 years later, and we had a lot of discussion with the referees, and it was refused by several journals. But now this paper has a lot of citations. Anyhow, Samoil was very interested in sterile neutrinos. And but in the last years, he became very skeptical about the existence of light sterile neutrinos, and this was for reasons of economy and simplicity, as indicated by the seesaw mechanism. So he was a rather strong believer in the seesaw mechanism. And for example, in this article, he writes that if light sterile neutrinos will be discovered in future short baseline and other neutrino experiments, in this case, our ideas about the origin of small neutrino masses will be completely changed. However, he emphasized that the question of the existence of light sterile neutrinos must be answered experimentally. And so he always emphasized that physical theories must be guided by experiment. And if you are interested in this topic, you can read these two papers. In the last year, he became interested in general relativity, and his last contribution to physics is a pedagogical review on general relativities, which appeared just a few weeks before his departure. Here I show a photo of his presentation in this colloquium that was held in Prague in occasion of his 90th birthday. And as you can see here from this slide, he is just talking about simplicity as a guide to the theory in physics. I must also mention that we made a very nice meeting in honor of his 70th birthday in Torino, where many friends came at the time in 1999. And in occasion of his 19th birthday, besides the meeting in Prague, there was also a meeting in Dubna, and you can see here some picture, and he received also some recognition from the director of Jean Mathieu. So to end this tribute, I would like to say to Samoil goodbye. We miss you very much, and it is nice to think of him as walking in the mountains as he liked to do. Thank you very much.
Thank you, Carlo, for sharing your recollections of Samoil Bilenky. As you said, he was here in Valencia in the 90s, and we have exceedingly good memories of Samoil. He was well appreciated in Valencia, not only for his high scientific level, but also because of his very warm personality. Thank you again, Carlo.
Thank you.
So let's go now to the regular session. So we start by the presentation by Valerio Formato of INFN Roma 2 about the direct measurements of cosmic rays from space. So Valerio.
Okay, thank you very much, and thanks to the organizers to giving me the opportunity to do this talk in place of Professor Bruno Bertucci, who unfortunately could not attend this conference at this very moment, but I tried to keep the spirit as close as possible to what she wanted to show to everybody. So the talk itself is about direct cosmic rays measurement from space, and just as a disclaimer, this will be from the point of view of an experimentalist. So apologies if we're not going to touch theory of cosmic rays, if not even a little bit during the talk, but it will be mainly a review of all the experimental results that have come out in the recent years. Okay, so let's start with what is the overall broad view of cosmic ray physics that everybody is taught, mainly in the university, let's say. So we have this stream of particles which is coming from the outer space into our solar system, and after entering the solar system, it will eventually, part of it will reach our planet, and only there our atmosphere and the Earth magnetic field will act as a shield. But this also means that these cosmic rays will interact with the atmosphere and produce a shower of secondary particles. And this is actually how cosmic rays came actually have been discovered in history. But this also means that if you want to study them directly, so without relying on all the products that are being produced in these showers, you have to go above the atmosphere. This is like the first obstacle you need to overcome in order to study directly cosmic rays. Once you do so, which is, by the way, no trivial task, because you need to put detectors either on balloons to take them high into the stratosphere, or actually go to space, which is where things get more interesting. You need to pay a lot and overcome a lot of technical difficulties due to the fact that you need to lift your detector by several hundred kilometers in altitude. So once you start to do that, you will discover that cosmic rays span a very huge energy range, several decades in energy and also in intensity, where basically part of the cosmic ray are at very, very, very low energy, are produced by the sun and are streamed by the sun. This is called solar wind, and also are accelerated by the sun in energetic events like coronal mass ejections and so on. But then you have a component that at higher energy, let's say from a few hundred MeV onwards, is mainly due to the cosmic rays that comes to the solar system from our galaxy. So these are called galactic cosmic rays. And even if at very low energies, the spectral intensity of what we call the flux, which is basically the number of particles per unit surface and energy, is distorted by the action of the sun from, let's say, some tenths of GeV onwards, you will see a very nice power law structure of this flux. But this is just the tip of the iceberg, because once you go look into more detail about how cosmic rays are made, how many species are there, what's the energy distribution of each species, you find out that this is the actual iceberg, which is huge. So basically you have all the elements of the periodic table in cosmic rays, but then you have also 1% component of electrons, and then you start studying the energy distribution of all the singular species, and you see that yes, more or less we have a power law, but the more you go towards high energy, you start to see spectral shapes, that deviations from the simple power law structure. But then you also find out that there is a very small amount of antimatter in cosmic rays, and then you start to wonder how this is produced. And then you remind, oh, there's the interstellar medium. So this antimatter could be produced by the cosmic rays traveling through the galaxy, interacting with interstellar medium, and some of the decay channels will produce antimatter, mainly positons and antiprotons. But then strange things start to appear, like there's too many positons with respect to what we thought there should be according to the distribution of the interstellar medium and the cross-section for the production of pions and muons that then decay into positons. And then you start to see that the flux of positons increases. So there are a lot of things that are still open in this field. We don't know what are the sources that are accelerating cosmic rays up to the TeV energy, and even higher ultra high energy cosmic rays actually go even 10 orders of magnitude above. How do they travel through the galaxy? This is also not so well understood, because there are also all these spectral features that come out of nowhere. And what are the interstellar medium properties? And is there new physics that is producing all this antimatter? And for all of you that do remember, 10 years ago, I was a humble student, but there was everything kind of started with this electron bump measured by the ATIC experiment. So there was an excess of electron pulse positons, because this was a calorimeter, couldn't understand, distinguish between the two. But then there was no such bump in Fermi-Lat and Pamela data. But then with Pamela, an experiment with a magnet that could measure positons, there was this famous excess. So this positon fraction, which is the ratio of positons to the total lepton content in cosmic rays, was going up in energy, which is not what is predicted by the theory of cosmic ray collisions. So everybody started talking about dark matter, because that's an easy way of producing antimatter in the galaxy. But then there is no such component for antiprotons. So either this dark matter is the term at the time was leptophilic, so it really likes to produce positons but not anti-quarks or quarks, or there's some kind of other sources, and people started talking a lot about astrophysical sources such as pulsars. So the situation now, let's say the most recent data about this is from the alpha magnetic spectrometer, which is an experiment, a very big cosmic ray detector on the International Space Station, is in this paper, the physics report of which came out this year, and it's collecting like 7 years of data, I think it was, and there's the a very detailed measurement of the electron and positron spectrum in the energy range up to 1 TeV. And you can see that these spectra don't have a very simple power law structure. They have a complex shape. Especially what was seen is that even the electron spectrum, which was thought to be well understood, has some spectral shapes. So in particular, it hardens at higher energy. And there is this clear hardening of the positron spectrum, which is attributed to some kind of source that is producing both positons and electrons, possibly in the same amount, measure, or close to 50-50 share. And even with a very simple heuristic model, you can actually try to isolate these terms and try to do some simple assessment of, is it really the same shape between the two, or is there something else, which is what was attended. What seems to be very interesting is that there seems to be a cutoff in the positon spectrum around 1 TeV. And this is statistically significant to the 4 sigma level using the AMS data. And this could mean that whatever the source is, there is a limit on the energy can accelerate positons, or this is due to the distance, because the leptons have very drastic energy losses while they travel through the galaxy. So at a certain energy, they cannot come from too far, otherwise they would have lost all their energy. And on top of this, we had also more recent measurements of the total lepton component, so electrons plus positons, which is usually measured with large calorimetric experiments like the Galactic experiment, also on the International Space Station, or Fermi-LAT and DAMPE, which are free flyer satellites with very big electromagnetic calorimeters. And here the scenario is a little bit complex, because there is kind of a bipartition of measurements into two groups. We have Fermi and DAMPE on one side, and CALET and AMS on the other side. We agree one with the other, but not these two groups. There is some tension between the data. But what seems to be the emerging properties about this is that this flux is also rapidly going down above 1 TeV. And this is very hard to explain with conventional diffusive models of cosmic ray propagation. First of all, because of the abundance of positons, which cannot be reproduced unless one starts to assume something really unphysical that doesn't fit with the rest of the cosmic ray data. But still, you need some kind of sources to make up for this missing flux of electrons and positons and electrons, because also the electron flux shows something like that. So dark matter, pulsar with nebulae, close or old supernova remnants, millisecond pulsars, there's a plethora of possible explanations around, and no clear smoking gun to distinguish one from the other. On the other side of the antimatter story, there are antiprotons, which on the other hand do not show any distinct spectral feature, but with respect to the old predictions, let's say from more than 5 years ago, this spectrum is kind of hardened than the theory could predict. But then it turns out that these predictions are really sensitive to which kind of cross-section you use for the antiproton production, which is not very well measured, because these antiprotons are well, let's say 1 TeV antiproton comes from roughly a 10 TeV proton interacting with the ISM, and we do not have experimental data 10 TeV. So there was a huge campaign and cry for help from the theory community to have a better understanding of the antiproton production cross-section. In this scenario, dark matter is not really a compelling explanation of the data. There's not really a lot of room for dark matter, and most of the theoretical arguments for it are actually even at lower energy than one would expect. And what is really striking actually is when you start to look at both antiprotons and positons, because they're both so-called secondary species, meaning that they are produced by the interaction of primary cosmic rays with the interstellar medium, but they are expected to have very different spectra, because the way that they travel through the galaxy is very different. Surprisingly, what you see is that at high energy, the positon to antiproton ratio is surprisingly flat and consistent with the value of 2. This is a very interesting puzzle, because this value of 2 is really close to the ratio of the production cross-section of the two species. But for this to be the explanation, it means also that these do travel in the same way through the galaxy, which contradicts a lot of fairly basic assumptions of physics of cosmic rays that we know. And then there's the, let's say, the rest of cosmic rays, which is the nuclear or hadronic component, which is split also into primary and secondary families. The primary is the one that are produced by some kind of astrophysical energetic event, like probably supernovae explosion, and injected through the galaxy, where they travel against the galactic magnetic field until they eventually some of them will reach our galaxy and be detected. And if nothing happens during this travel, we can label them as primary, but if they interact and give birth to other species that are not present in the source of acceleration, these will be called secondary cosmic rays. And what's interesting is that if studying secondaries and primary, you are basically doing a tomography of the galaxy. You're studying how much matter there is in our galaxy, how much of it is sampled by cosmic rays, and so on. And approximately these cosmic rays, the distance they travel is actually limited by both the diffusion in the galactic magnetic field and the cross sections for fragmentation. So you can expect that heavier nuclei come from closer to our galaxy, and the higher you go in energy, the easier it is for cosmic rays to escape our galaxy. So so you can estimate these parameters from the data itself, but roughly speaking, what helps in studying the cosmic ray propagation is using many different species, because you sample different volumes from the galaxy and also different rigidities or energies in studying this. And surprises started to come in this sector of cosmic ray physics around, again, 2011, which was a big year for cosmic rays, when the Pamela paper about proton and helium fluxes came out, where there was the first detailed measurement of the spectral features in cosmic ray, which were deviating again from the single power law. And there was this actually a very clean break, so a regime in which you have one spectral index at some energies, and then it changes completely to some other value above a threshold value. And this was kind of important because there were spectroscopic measurements at lower energies, which were pointing to some value of the spectral index for proton and helium. And then there were calorimetric energies measurement at higher energies, which had another value, probably non-compatible even with what measured by spectrometers. So this was the first measurement that which actually was bridging the gap and showing that actually both were right. So the flux itself is changing shape at some around a couple hundred GeV of rigidity. And this was confirmed later on by AMS around 2015, when the same measurements were performed. And this poses some questions. So where is this spectral break coming from? Is it present in all the species? Is it the same in all the species? And we know that proton and helium are just, again, the tip of the iceberg when you study cosmic ray nuclei, because they are the most abundant species, but they are not the only one. There's basically the whole periodic table in cosmic rays. So is this something that happens also for heavier nuclei? And the situation in 2019 is a bit more complete, because a lot of papers from AMS came out in these years, so let's say from 2015 to 2019. So basically, we now have the measurement of the fluxes of cosmic ray nuclei from hydrogen protons up to oxygen, and we have all 8 of them up to the 3 TeV of energy. So we start to see some patterns. When we put everything together, we start to see that helium, carbon, oxygen, they have mostly the same spectral shape with different normalization, of course, but the spectral shape is mostly the same, above 50 GeV, where we don't have the effect of this heliosphere distorting the fluxes. There is the same spectral break for all 3 of them at around 300 gigawatts, sorry. And then we have the secondaries, which are lithium, beryllium, and boron in this sample of elements, which are mostly secondary species. Some of them are close to being pure secondary and also have a tertiary component. And they also show the same spectral shape, about a few tens of gigawatts. And they also show a spectral break at 300 GeV, which is the same for all 3 of them, but is different from the spectral shape of helium, carbon, and oxygen. In particular, the magnitude of this break, the amount of change, is double, which is actually a very nice feature, which is predicted by all those models that attribute this change to a change in the way cosmic rays travel through the galaxy, the so-called propagation scenario. Because this feature could even be originally at the source, this spectral feature, and then is propagated throughout the galaxy, or you could have a smooth power law spectrum at the source, and then this feature is introduced during propagation. And if it is the case, you expect that this amount is double in secondaries because they basically travel twice. You have the first distortion when the primaries are traveling, and then you have the interaction, and then the secondaries are also propagating through the galaxy. So this effect kind of doubles in magnitude. But this is very naive explanation. And then we have nitrogen, which is present at the source, but not by a large amount. And it's also produced during a cosmic ray propagation. This is a kind of in-between situation when there's actually two components, one which is primary and one which is secondary. And we also started having more measurements about proton and helium fluxes, and which also extend the energy reach up to hundreds of TeV, which is the case of the papers by the Kale collaboration and Dumpy collaboration. So here we have also calorimeters which are starting to take over and pushing the limit of these measurements to higher energy. And we start to see that the situation is even more complex, because at around 10 TeV or so, these fluxes are starting to soften again after the hardening. And this makes the interpretation even harder than it was before, because now you have possibly you're seeing the contribution of some kind of sources of cosmic rays which might be close by, or some kind of source family which is producing cosmic rays in the same way, and these are in addition to the ones produced by conventional sources. But again, the shape of this bump, let's say, is heavily dependent on the source type, spectrum, age, and distance. This is very these are all unknowns that we cannot really test for. Or this is a new population of cosmic rays, and this is due to different environments that these cosmic rays are sampling during their life. The Kale collaboration also published a paper with carbon and oxygen, so they were able to measure the same hardening that was measured by AMS a few years earlier. And they do also see that the spectral shape of carbon and oxygen is quite similar one to the other. So this is a confirmation of the previous measurement. And now, let's say, this was the situation. Now also, the AMS collaboration is starting to study higher and higher charged nuclei. In particular, once you go in order of abundance, which is what sensibly you would do, because this statistics makes it easier if you have a lot of events to study. There was a paper in 2020 where the flux of neon, magnesium, and silicon, which are the three most abundant primaries after oxygen, were studied. And again, there was another surprise, because you would expect that since these are primaries, they would share the same spectral shape as helium, carbon, and oxygen, but they do not. So they are kind of clustered all together, but separate from helium, carbon, oxygen. So probably this is a slightly different family of primary cosmic rays. But what is causing this different? It is so far unexplained, or it is not clearly understood yet. And then again, in order of abundance, another primary cosmic ray, which is species which is really interesting in studies, is iron, because again, iron would sample a more local component of the galaxy, so you would start seeing things differ, maybe due to the way the galaxy changes when you go out of the solar system. And there were two papers in this recent year from the AMS collaboration and from the Kale collaboration, where there was the measurement of the iron flux up to the TeV region with high precision, which was really the first precise measurement of this flux at the TeV. And once you overlap the iron to the other primaries in cosmic rays, then now again the iron seems to follow here helium, carbon, oxygen. So it would appear that it belongs to the first family of primaries in cosmic rays. But you start to see that the more you dig, the stranger things start to appear. And there is a word of caution when people analyze this data, because I didn't comment, because that there's nothing to comment at the moment, but there is some tension between the AMS and Calet measurements of the nuclei fluxes, in particular carbon, oxygen, and iron. There seems to be an issue with normalization between the two experiments, which could be due to the effect of the hadronic cross-section of the cosmic rays with the detector playing a role in possibly explaining this difference, but there's no way of so far no explanation for this tension yet. But once you can just adjust the normalization of the two to make them agree, and you can actually see that the shape is in quite good agreement between the two experiments. Lastly, there was the measurement of the fluorine fluxes, so starting to fill the void in the species catalog of cosmic rays. And again, fluorine is a mostly purely secondary species, but is acting slightly different from lithium, beryllium, and boron, especially once it's compared to its progenitor, so the species that is fragmenting into fluorine, which is mainly silicon. And you compare this with how boron compares to oxygen, which is its main progenitor, and you start to see that these two secondary to primary ratio are kind of different. So there's something, again, strange going on with the family of cosmic rays, which is between fluorine and silicon, which is different from the more abundant cosmic rays from helium to oxygen. And then lastly, the very last publication, which came out a few months ago, actually, it's very recent, fresh from the oven, is the measurement of the sodium and aluminum flux in cosmic ray, again by DMS collaboration. And these are two species that, similarly to nitrogen, have a mixture component of both primary and secondary component overlapped together. And you can see that this is reflected on where they place on this giant atlas of nuclear cosmic rays in the TeV region. They also go in between secondaries and primaries, right, but nitrogen is. And again, so the more you take data, the more you analyze it, the more you start looking at things together, the more this picture becomes complex. And it can get even more complex if you start looking at topics that I do not have the time to discuss, unfortunately, which are some of these nuclei also have different isotopes composition. So helium is made of helium-3 and helium-4. You can study that. Lithium-6, lithium-7, beryllium-7, 9, and 10. And then you can study this as a function of time and see how the changing in the heliospheric conditions affect these fluxes. So this is a really complex subject. And unfortunately, I do not have the time to go through all this. But for the future, there's hope to better understand all these things due to some new experiments which are being designed or are ready to fly in the next year on balloons and or space stations. And for the far future, there are even more, how do you say, ambitious projects of putting new spectrometers in space with superconducting magnets, which is a really hard challenge to overcome, but could eventually open a new era in cosmic ray physics. So with that, I thank you for your attention, and I will stop here since I'm almost run out of time, and I leave the conclusions here up to you for reading. Thanks.
Thank you very much for this summary of this complex, very exciting situation concerning cosmic rays. For the audience, you know that you can ask your questions through the Q&A section, and I will convey your question to the speaker. So I don't see any question. I have one myself, very general, probably very vague, but anyhow, what's your feeling about where progress will be made in this field? We need more statistics? Is a question of a better description of propagation, or?
I'll tell you okay. Disclaimer, this is my opinion. It is not super controversial, but still my personal opinion. We do not need more statistics per se in the experiments. We either need to reach higher energies, in which case, okay, yes, some of these measurements are still statistically limited, but only in a few bins. Mostly these are very precise measurement down to the few percent level of systematics uncertainties. So really the challenge is understanding your experiment rather than gathering more data. From the theoretical side, there are a lot of unknowns because you cannot go and directly measure, sample the whole galaxy in any way. So you have always an approximate description on how the galaxy is made and the matter content and the distribution of it. And also the cross-section that are producing most of these cosmic rays, especially the secondaries, are not really well measured in the hundreds of GeV range. So there are a lot of uncertainties from the theory side. And there also have been some requests for new measuring campaigns for some of this cross-section, which are actually starting in this time frame, in the present time frame. There's some from the NA61 experiment are contributing to this, and there are other plans for some part of the COMPASS collaboration is joining a project to also study these kind of things. But mainly you wanna from the experimental side, you want to rather extend the energy range rather than shrink the error even more, because you're already down to a few percent level on the systematics. So apart some cases which are statistically limited, where we could help, you actually want a new measurements. And here, depending on what kind of instrument you have very different kind of properties and capabilities. Calorimeters are easy to make and are easy to extend the energy range, but they pay the price of higher systematics because your energy measurement is depending on the Monte Carlo simulation. So you have a huge source of this systematic that comes from there, and from the fact that some of these processes are not measured in accelerators because we don't have the energy reach yet. On the other hand, spectrometers are harder to understand and maintain, and they're also smaller, usually, but you have the plus of having a much more controlled instrument.
Mm-hmm. Okay, thank you. What time scale are we talking about in these detectors on the space station? It could be done this decade, or could
yes, some of them, like the HERD experiment, is expected to launch by the end of next decade, and is in design phase, and there are some prototypes being built as we speak now. I don't know about the Tiger ISS. I don't know if there's a time frame. Balloons are easier to make, of course, so there are several proposed for next year. But for these giant experiments here, these are targeting more like 2050 and let's say next to next decade, because these are really, really, really conceptual in nature.
Okay, thank you very much again, Valerio, for your nice talk. And then we move on to the next talk by Justin Vandenbroucke of the University of Wisconsin, that will talk us about high energy neutrinos. Can you see you, Justin? Okay, so you're sharing? Great.
Hi, can you hear me and see the screen okay?
Perfectly. Everything is all right. Thank you.
Great. Hi. Thank you to the conveners and organizers for the invitation to discuss high energy neutrinos. High energy neutrinos in this context means astrophysical neutrinos. So here's a big picture context to start with. This is from a review by Formato and Zeller of the cross-section, the various interaction cross-sections of neutrinos over many orders of magnitude and energy that you can see here. And so if we start at the very low energy, overlaid on top are the sources of where we might find such neutrinos generated throughout the universe or here on Earth. At the lowest energies, of course, we have cosmic neutrinos from the Big Bang, relic neutrinos. Then we have, reaching into the MeV scale, we have neutrinos that are commonly used, MeV into GeV, for neutrino particle physics studies, including geoneutrinos, reactor-generated neutrinos, solar neutrinos, atmospheric, and then getting into the astrophysical cosmic regime, we have supernova neutrinos. At the higher energies at the GeV scale, we can also study human-made neutrinos from accelerators. The focus of this talk is high energy neutrinos at these very high energies at the TeV and higher energy scale, maybe a little bit below TeV, high GeV up through TeV and PeV, PeV being 10 to the 15 electron volts. And these are generated most likely well beyond the solar system throughout the galaxy and even throughout the universe, extragalactic sources. The challenge experimentally is that the fluxes, of course, are falling steeply as you go to these very high energies. They're much more rare than at the low energies. The positive thing is that that's offset by the increasing cross-section. So you can see the higher cross-section of these high energies compared to the lower energies that are used for particle physics studies. What are the science topics that we're interested in doing with these high energy neutrinos? One of the most exciting applications is multi-messenger astrophysics. And that's this new and growing idea that we can study the universe not only using the electromagnetic spectrum, which has proven very successful across, again, many orders of magnitude in photons, but now we can do parallel studies using the new messengers, cosmic rays, neutrinos, and gravitational waves. And the newest comers on the scene, of course, are gravitational waves and neutrinos, which have only been used for this purpose in the last few years. Here's an illustration of a possible accelerator out in the universe. Maybe it's a large hadron collider, very large, very far away. And it's accelerating particles, producing hadrons and neutrinos and gamma rays. The hadrons would be cosmic rays in this case. There's a proton here illustrated as an example. It propagates from the accelerator, but it's deflected by magnetic fields as it propagates. And so it might be detected on Earth from this direction in green, but really it came from the direction to the upper left. So we can complementarily study this source by using not only the cosmic rays that come from it, but by using the neutrinos and the gamma rays, which propagate undeflected from the source. Even among the gamma rays and the neutrinos, there's also good complementarity. The neutrinos are harder to detect and detected in lower rates. On the other hand, in addition to being undeflected by magnetic fields, they're also not absorbed by matter or radiation. So what are the scientific studies we can do with multi-messenger astrophysics? One of the most exciting is studying where and how these cosmic rays are produced, which again is difficult due to the deflection by the magnetic fields. Neutrinos are produced in hadronic interactions. So wherever we detect neutrinos, there's either hadronic processes going on or something exotic, such as dark matter interactions. A quantitative view of this is shown in this diagram. This is the flux scaled by energy squared of the diffuse signals for gamma rays, neutrinos, and cosmic rays. And you can see that they all follow steep power loss spectra, and they are detected so far over complementary energy ranges. Gamma rays at the GeV up to TeV energy scale, neutrinos at the TeV to PeV energy scale, and then extremely high energy cosmic rays in the 10 to the 18 up to 10 to the 20 electron volt scale. And so they have similar shapes, but they're offset in energies, and the normalization is similar. And when you work out the fact that this is on a log scale and scaled by E squared, the fact that they're on a vertical axis here at comparable levels indicates that their flux reaching the Earth and therefore their local energy density is very comparable among these. So that's very intriguing. That implies there's some kind of connection between these different messengers. There's likely some deep connection between them, but it's not a straightforward connection. If you image the sky in these different messengers, there's no clear correlation between the different signals. And so they really are complementary. How do we do this science? We use neutrino telescopes. I'm focusing again on the high energy up to very high energy range of neutrinos, focusing on this astrophysical context, in particular multi-messenger astronomy. And so we use neutrino telescopes. This is all using the optical Cherenkov technique in water, either liquid or solid water. There are other techniques that can work at even higher energies, but I'm going to focus on the optical Cherenkov technique for today. And there's a growing number of these neutrino telescopes around the world. I'm a member of the IceCube collaboration. I'll choose some examples from IceCube. IceCube is at the South Pole. It's a cubic kilometer of instrumented ice. When a neutrino interacts in or near the detector, it produces secondary charge particles which emit Cherenkov radiation, which can then be detected by this array of photomultiplier tubes to measure the energy and direction of the original neutrino. There are other projects operating around the world. In the Mediterranean Sea, in liquid water, there's Antares, which has been running for over a decade. It's a smaller instrumented volume, but has a complementary view of the sky in terms of a view of the southern hemisphere looking through the Earth compared to ice cube looking through the Earth up at the northern hemisphere. I'll quantify that in a minute. Also under construction and now operating and producing results is KM3net, also in the Mediterranean Sea. It will eventually be over a cubic kilometer of instrumented seawater. Another project also under construction, aiming towards 1 cubic kilometer, is in Lake Baikal, and that's Baikal GVD. Finally, there's a new proposed project, which is in the Pacific Ocean. There's a demonstrator called STRAW, and there's a future project proposed named P1. What do the events look like in these neutrino telescopes? Here's an example of a neutrino-induced muon. It produces a long, straight muon track. Clearly, it's easy to calculate the direction of that muon and therefore of the neutrino. It's a bit harder to calculate the energy, but there are also complementary interaction channels. For example, an electron-flavored neutrino interacting to produce a cascade from an electron produces a shape like this. We call that a cascade or a shower, and it's easy to measure the energy of this, a bit harder to measure the direction. So there's some complementarity between the different channels. There's also an interesting signature of a possible tau neutrino, which could interact to make a tau lepton, which travels a relatively large distance, maybe tens of meters, compared to the accelerator context of the tau track length in these detectors, and then decays to produce a second signature. So this would be a so-called double cascade signature. In tracks, depending on the medium, we can determine the direction of the neutrino with a fraction of a degree angular resolution, and for cascades, a few degrees. What do the signals look like? It's important to point out that these are very background dominated experiments. So they're using sophisticated statistical techniques, including likelihood and machine learning techniques, to pull signal out of background. The main signal that they all detect is atmospheric muons, not even neutrinos, but muons produced by cosmic rays colliding with the atmosphere. And then a smaller component is atmospheric neutrinos, again, produced by the cosmic rays colliding with the atmosphere. You can see rates here for a typical cubic kilometer neutrino telescope. And then again, a smaller component among the total neutrino signal is the astrophysical signal. So we're trying to pull an astrophysical neutrino signal out of an atmospheric neutrino signal. We can do this thanks to the energy and angular distributions of the signals and backgrounds. So here's again an E² times flux spectral diagram. You can see the atmospheric spectrum is steeply falling. The astrophysical spectrum has a harder spectrum and sticks out above the background. And then we have a prediction of an even higher energy signal that I won't talk about in this talk. So we're looking for this green astrophysical signal on top of the blue atmospheric background. That's for distinguishing atmospheric neutrinos from astrophysical neutrinos. And then we can, of course, also distinguish them from the muons using some sophisticated veto techniques, but especially using the Earth as a filter. And so if you look at the downgoing direction, you have this huge atmospheric muon background, but if you look at the upgoing background, the Earth filters out the muons and leaves you with neutrinos, including both atmospheric and astrophysical muons. Here's a quantitative view of the complementarity in the sky coverage of the South Pole view compared to the Mediterranean view. Here's a 2D phase space of energy of the detected neutrinos versus sign of declination. So the right hand is the northern sky, celestial sky. The left hand is the southern sky. For the South Pole, for ice cube located at the South Pole, this view doesn't depend on what time it is, what time of day, whereas for other locations off axis, the exact sky coverage on the celestial sky varies as the Earth rotates. So this is averaged over that effect, and you can see the ratio of the effective area of ice cube to Antares, blue regions of this phase space where ice cube is more sensitive, red regions where Antares is more sensitive. And so you can see that complementarity. After ice cube was constructed and operated for the first year, there were a couple of interesting events that were discovered pretty quickly. And these are PeV events, 10 to the 15 electron volts. And there were a couple of these first discovered. And those two events alone were such high energy that it was very unlikely that they came from an atmospheric background. So that was enough for nearly 3 sigma evidence of astrophysical neutrinos. With a lower background search technique, 28 additional events were found, and so this raised the significance to above 4 sigma. Now, so these are event views of these example very high energy events spanning, again, a linear length of a kilometer. It's a little bit hard to visualize what these huge events look like. So here's a visualization of one of the same events overlaid on top of my campus in Madison, Wisconsin. And you can see what this looks like above a college town, spanning the entire campus and beyond. So these are really massive depositions of energy from astrophysical neutrinos. This is using a technique that we call the high energy starting events. They're starting in the sense that they start inside the detector, so there's no track before they interact within the detector, and then a track begins or a cascade. And so we can say with high confidence that these are astrophysical. There's a complementary search technique which uses the idea that I mentioned before, that the Earth filters out atmospheric muons, leaving us with neutrinos, and then we have to use energy to separate the astrophysical from the atmospheric neutrinos. And when we do that, we get this experimental data, which you can see looks very similar to the schematic I showed earlier. So we see the atmospheric signal in these data points and a fit to them in this red-pink color, sticking out above the atmospheric background in blue. So these are using 2 very different interaction and detection techniques, detecting a signal that looks compatible in terms of the spectral shape and normalization between the 2. So I want to pause for a minute now that I've described the methods of these neutrino telescopes and the total astrophysical signal that they've measured. I want to pause and think as a group a little bit about what's producing them. So if we can take a minute, if people could type into the chat what they think is producing these neutrinos, and then if the chair could read a few examples, that would be nice, that we could brainstorm as a group together. What ideas do you have of what's producing these neutrinos?
No suggestion for the time being, which is surprising.
Okay.
Come on.
Give people a minute.
AGN.
AGN, okay. Active
says,
galactic nuclei.
Right. Anything else that comes from Luca Latroni?
Thanks, Luca.
Now I have AGN again. Some other suggestions, something with a strong electric and magnetic fields, I would assume. Well,
Okay.
that's pretty general. That was by Giulietta. Let me see, Grusco. Then Marek Matas, high energy muons accelerated conventionally.
Okay, so you could accelerate a muon and then have it decay.
Right.
And this general
else?
concept of electric and magnetic fields, I agree that's important extrapolating from human-made accelerators. We need to somehow confine the particles in the accelerator while they're being accelerated.
Then starburst galaxies from Dario Grasso.
Okay, thanks, Dario. Yeah, starburst galaxies with very high rates of star formation, a subset of star-forming galaxies.
Tidal disrupting black holes by Jassaman Farzan. Magnetars by Andre Saputra. Jet from Quasar, Animesh.
Okay, great. Thanks, everyone. I think we can go on for now. Yeah, that's a great list, and that's what probably most physicists and astronomers would come up with, some of those items as the first ideas. So I'll go through my list. Gamma ray bursts we didn't get to yet. Star-forming galaxies we did. Starbursts are a subset of those. Active galactic nuclei, including blazars. If we extrapolate from the electromagnetic skies, these are some of the most energetic and interesting objects that we might expect to be important in the hadronic sky as well. So these are all important, especially if we focus on the gamma ray sky. Blazars are very important to GeV and TeV gamma ray astronomy. So that's a good candidate. Those could be time averaged, or they could be bright only when they're flaring in neutrinos. Galaxy clusters, also good gamma ray and neutrino candidates. Supernovae, we know they produce MEV neutrinos, but maybe they also accelerate TeV or produce TeV neutrinos. Moving closer to the galaxy, there could be diffuse processes that produce gamma rays along with, or neutrinos rather, along with the gamma rays. And there can be discrete sources that produce neutrinos along with cosmic rays. Generalizing from gamma ray bursts, there could be binary black hole or neutron star mergers that produce neutrinos. Galactic novae they're a very old source class electromagnetically, but it's only discovered recently that they're also very good particle accelerators. Tidal disruption events were mentioned. Fast radio bursts are a new astrophysical transient that's very exciting, and there's some models for neutrinos from them, and dark matter. So I'm going to show some example searches from some of these. I want to start with a general all sky search. So I presented the diffuse measurements or the total astrophysical neutrino flux measurements earlier. The first thing you want to do then, if you want to search for sources, is just make a map of the sky. And if you look through the history of astronomy, that's what was done anytime a new wavelength was opened up. You make a map of the sky and see what the shape of it looks like. Right away, you see that it's very smooth. It's consistent with isotropic. And so that tells you that it's likely dominated by an extragalactic signal. Not only is it very isotropic, well, it's very isotropic, and therefore, whatever sources there are many of them. I'll quantify that in a minute. But there's probably a large number of relatively dim sources rather than, we can tell right away from this plot, they're not just a handful of sources that are producing the flux. So this is a map of the p-value at each location on the sky, highlighting the most significant spot in the north and in the south. And this is not using any particular source catalog among those we named a minute ago, just looking across the entire sky with IceCube. So if you quantify this, comparing the sensitivity to individual point light sources, comparing that to the total flux that's been measured, we know that there are at least 100 sources, maybe a few hundred if you quantify that more precisely. If we zoom in on that brightest spot in the north, you can see this color scale again is the local significance or the p-value. There's also an interesting known astrophysical object located consistent with that direction, which is NGC 1068. NGC 1068 was also part of a list of sources that we studied with IceCube. And so that was 110 different objects. And we basically do a catalog search where we look for emission from any of those individual objects. And we do a test where we see if any subset of them could be significantly emitting. And the most significant subset that we find consists of the 4 most significant sources, which are in an aggregate sense, 2.9 sigma significant for emission from for time integrated emission from these 4 sources. Quantifying this a bit more, here you can see the sensitivity as a function of declination on the sky for 2 different spectral models, either e to the -3 or e to the -2. And these crosses and pluses mark for those 2 spectral assumptions the upper limits from individual sources in this list of 110 sources. And you can see these 4, we set upper limits because we don't have significant time integrated emission from any one of these rising to the 3 sigma level. So we set upper limits, but we do have excesses from those 4 sources. And you can see them here in these crosses. So they do have larger upper limits because of those excesses. Okay, gamma ray bursts are also an important individual source class. There have been systematic searches by both Antares and IceCube. Here you can see on the left the constraints in this energy spectrum plot by Antares searches for gamma ray bursts. You can see the search for the individual about 800 GRBs that they search for is this upper limit in solid red. If you scale to try to describe the entire diffuse or total astrophysical neutrino flux, you get this dashed line. And you can compare that to the total flux measured by those 2 complementary techniques by IceCube in green and blue. You can generalize the spectral model to describe it by an energy break and a normalization. And if you do that in an IceCube analysis, you can exclude this large primary space by IceCube. And so if you interpret this in terms of needing to explain the total ultra energy cosmic ray flux, you cannot do that using gamma ray bursts. because there would be a brighter neutrino signal. Now, in the last few years, an especially important topic has been the rise of time domain astronomy, and in particular, real-time alerts by instruments, including neutrino telescopes. So after learning to do all of these analyses offline, we then sped them up doing event reconstruction and public alerting of individual events for the last 5 years. So each of these are the first 10 events that were publicly published. Each was announced within 1 minute of detection. So from interaction in the ice to reconstruction by the computing farm there to publishing on the web. The 10th was particularly interesting. In 2017, it was this event pointing nearly towards the horizon, a declination, or towards the celestial horizon equator, with a declination of about +6 degrees, a neutrino energy of several hundred TeV. And again, it was published less than a minute and about 43 seconds after interaction. As was done for many of these alerts, a whole suite of astrophysical observatories followed up and searched for anything interesting in this direction. And within about a day, the Fermi-Lat pointed out that there was a flaring GeV blazar in that direction. So here in the background color scale, you can see the Fermi-Lat sky map, along with the direction reconstruction of the neutrino. And after that, the MAGIC TeV telescope also pointed in that direction and detected the same blazar for the first time. So this altogether constitutes evidence that this is an astrophysical neutrino source. There were 2 papers that were published, one describing these various multi-messenger observations that I mentioned, and one describing an archival analysis by IceCube that found modest significance for a time integrated or time average signal in that same direction, as well as a flare in neutrinos that lasted about half a year, a few months, from 2014 to 2015. Now, what I've described so far is neutrino telescopes alerting other observatories about an interesting neutrino event. We can also do the opposite, which is when any other instrument detects something interesting going on in one region of the sky. One great thing about neutrino telescopes is they observe in all directions at all times. And so we can quickly run an analysis pipeline that searches for a neutrino signal in that direction. As an example from IceCube, here's a set of 58 of these analyses that have been done as published in this paper, and the distribution of p-values from those analyses. You can see that the significance distribution matches the background expectation for these individual analyses. And we've done those for some particular interesting individual astrophysical transients, including very bright gamma ray bursts, including those detected, for example, by TeV instruments. We can also follow up gravitational waves. So when a gravitational wave is detected, we quickly search for a neutrino counterpart. Again, we can do that in the full sky. We can do that with all of the neutrino telescopes, including IceCube and Antares, and even using Auger as a neutrino instrument. So far, there has not been any signal detected. Here are from the first few gravitational waves during LIGO Virgo observing run 1. During the most recent observing run 03, we were running in real time. And so the rate increased dramatically, as you can see on the left. And we could run our pipeline immediately within a few minutes every time a gravitational wave was detected. And if we saw any neutrino candidate events from the same direction, as illustrated in this example, red is the gravitational wave sky map, blue are the neutrino candidates. And in this case, there was one coincident with the gravitational wave localization region, about 1% p-value, but that's without accounting for trials across multiple gravitational waves. If you summarize this, here's the data from 01 and 02. We also have analysis from 03. You can summarize this in terms of this multi-messenger overlay of measurements and upper limits. In crosses are the total energy from the progenitor system for these different gravitational wave events. In the crosses are the total radiated energy. And then in green is for the case of the binary neutron star merger event that was detected with a counterpart gamma ray burst. You can see the measured gamma ray energy. So these are all scaled by distance to calculate the total isotropic equivalent energy emitted at the source. And then you can see in triangles are the neutrino upper limits falling between the gravitational wave measurements and the gamma ray measurements. Fast radio bursts, as we discussed, are an exciting new source class. We don't know if they emit neutrinos, and we don't know if so on what timescale, if it's connected to the prompt signal in the radio, or if it's on longer timescales. And so we can do this model independent search over a range of different timescales, setting upper limits at each timescale. So here you can see an analysis by IceCube with a few dozen events of FRBs. And then the number of detections is growing quickly. So there are also some extrapolations of the sensitivity to more and more fast radio bursts. Antares has done similar studies. Here are some upper limits from individual FRBs by Antares using different spectral models on the left, and then also excluding this phase space in isotropic equivalent energy as a function of distance. Coming closer to home within the galaxy, here's an example of a galactic source class that has been studied. Here's again an Antares analysis searching for flares from X-ray binaries. These are binary systems within the galaxy that flare occasionally. There's sometimes, some of them are considered to be microquasars, a local galactic analog of extragalactic quasars. So here's a search for neutrinos coincident with X-ray flares. None detected so far in neutrinos. So that was kind of a sampling of individual source classes that we've studied. We've seen that the state of the art today is that we've seen this diffuse flux. We've measured it, we've discovered it with high statistical significance, measured its spectral shape and isotropy, and we're now starting to see evidence emerge for the first source, individual sources and therefore source classes, including the blazar that I mentioned, this TXS 0506 object that was detected in GeV and TeV. And so the question moving forward is, are there many dim sources or few bright sources? We know that there are not just a handful of bright sources. There must be at least on the order of 100 sources, and we can quantify in this diagram. So the luminosity on the horizontal axis, the number density of sources on the vertical axis, and you can see these different candidate source classes and the constraints from IceCube in blue, and then going towards a future possible upgrade called IceCube Gen 2 in green, cutting deeper into this phase space. That's for in the case that these sources are steady, they might also be transient, and you can make a similar diagram for transients. So looking to the future, there's that IceCube Gen 2 instrument that I mentioned. Here's what it would look like. You can read more about the conceptual design and the sensitivity of IceCube Gen 2 in this white paper. And here's a projection of what the measurement of the diffuse astrophysical neutrino spectrum might look like, extending, improving the precision in the energy range where we have measured it, and then extending it to much higher energies. We've started the first step towards IceCube Gen 2, which is called the IceCube upgrade. This is a funded project that's under construction. This is an infill of IceCube, which will improve our medium to low energy neutrino physics and astrophysics capabilities, but also importantly, it'll improve our calibration capabilities. By studying the ice properties in depth, we'll be able to calibrate the detector and rerun those calibrations on the full decade plus of data to rerun archival analyses and also improve real-time studies into the future. That's the future in the Southern Hemisphere. In the Northern Hemisphere, CAME3net and Baikal GVD construction are proceeding quickly and smoothly. There's first data from CAME3net already. Here's an example on the left. Detection of both atmospheric muons and atmospheric neutrinos shown in this upgoing region of this spectrum, this directional distribution by CAME3net. Projecting to the future, here's what's expected from the two locations of CAME3net, a low energy array and a high energy array, much higher effective volume than Antares going into the future. So to conclude, here are these new so-called windows on the universe, the neutrino, the very high energy and high energy gamma ray, and gravitational waves. And they're really complementary. They show different views of the universe, which is really beautiful and what we always wanted with multi-messenger astronomy. It might be a little bit surprising how different the views are. And so the challenge now is to reconcile them and to get them to make sense with respect to one another. So neutrino astronomy is now a reality. We've measured this total diffuse astrophysical neutrino signal. We're improving the quantitative characterization of it in terms of its spectral shape, its isotropy, and its flavor ratio. We're starting to see evidence for individual sources coming from different source classes. And if you learn from the electromagnetic sky, there's a huge diversity of source classes and phenomena. So it won't be surprising if we see the same in the hadronic sky. So that means there are likely different source classes. The big question that I'm excited about is what are they? And the great thing is that we have new instruments under construction and on the horizon that will answer this and many other diverse scientific topics with neutrino telescopes that I didn't have time to get to. Thank you.
Thank you very much, Justin, for this wonderful talk. You have a question by Mariano Chavez. Can several neutrino telescopes observe neutrinos from the same source at the same time and complement each other, similar to what happens with gravitational waves?
Yes, they can. So even though with different locations on the Earth, they have complementary sensitivity on the sky, they also have good overlap. And so every neutrino telescope can see the full sky. It's just more sensitive in some regions than others. And here's an example. So for that TXS blazar, for example, GVD has searched for neutrino events from that same direction at the same time as that high energy alert that triggered the other observations. In this case, there was no detection, but of course, we're excited about a future where we will discover the same phenomena with different neutrino telescopes and be able to combine the information.
Thanks. Any other question? Julieta Grusco says, on slide 32, how do these exclusion capabilities change if you have a single source type that can emit both transient and diffuse neutrinos, as the blazar did?
Yeah, that's a great question. There's some difficult situation to understand what's going on with that blazar. The statistics are low, obviously, we need more data. So there's this marginally significant evidence for both time integrated emission from that source and a few month-long flare. And that is done in other wavebands, in other messengers, I should say, in the electromagnetic, both in gamma rays and in other bands, where you can study both the time integrated signal from blazars and the flare signal. And I would go about it as basically treating them as two different source classes. So you can think of one as steady and then one as a transient. Of course, the reality is probably more complicated, where it might be a continuously variable sources where there's really no such thing as a quiescent state. It's just always varying. But that would be a way that I would put those two on the same plot.
Okay. Any other question? I got one prompted by your first slide. There is a huge peak. And have you any new candidates of glacial resonance events or?
Yes. Let me find it. I guess you say new, so I'll just tell the audience that there's one. There are no new ones beyond the one that was published. But here's this publication from just a few months ago where we have our first candidate. And so the glacial resonance is this large cross-section for neutrino anti-electrons interacting with atomic electrons in the ice. And we do have one event that's compatible with that energy so far.
But nothing new that can be announced in this conference now. So Dario Grasso has a question. Is the evidence of a diffuse component from our galaxy increased?
No. Just show a slide on that. Yeah, there are a lot of other science topics I didn't have time for, so thanks for that. Here's still the state of the art. This is a combined ice cube and Antares analysis. And I'm sure, Dario, you're familiar with this analysis, so that I'll just tell others. Here are some models in the gray bands, and then we have upper limits from Antares and Ice Cube. And so you can see they're getting very close to the diffuse galactic upper limits. I think there's been a lot of exciting news from very high energy and even ultra high energy gamma ray telescopes recently, showing that there's definitely very high energy activity in our galaxy, as expected from cosmic rays and now seen in gamma rays. And the next step will be to see it in neutrinos, both in discrete sources and in diffuse emission. But we haven't detected it yet.
Okay. No other question. No, so let me thank you again, Justin, and also the rest of the speakers of this session. And we come back at 4 Central European time. I remind you that we have to leave now and to reconnect again at 4. Thank you.